Okay, AP Chemers, this is another screencast by Lazar. What you'll notice is I've got a 0.1 molar solution of Na2SO4, sodium sulfate. And inside this solution, I've put a drop or two or three or four of universal indicator. Okay, so there's some universal indicator there. This is sodium sulfate. 0.1 molar sodium sulfate. And I put the drops of universal indicator in there. It was green before, and a little bit yellowish to, or kind of a yellowish green, maybe an orange. Okay? And I should probably remind you of the colors for universal indicator, because universal indicator, we used that on a lab earlier in the year, or the demo, Alka-Seltzer and vinegar. So I've got it right here, so you can see the colors. Kind of, this looks like kind of yellow-orange. It's somewhere around maybe a pH of 5 or 6. Okay, that's what universal indicator does. And I've got a 9-volt battery here, and I've got some pencil lead. So what I'm going to do with the pencil lead is I'm going to attach it to the to our electrodes here, and have that reach down into the solution. And let me get another one of these and attach it to the other electrode. Oops, that just broke. That's why I got a bunch of extras here in case they break, because they're very fragile. And let me put another one in here. Okay, so we've got a 9-volt battery, and that 9-volt battery is providing a current to run through the solution. Okay. Now, I've got another 9-volt battery here because sometimes it's a little bit hard to see what's going on. So I'm going to move in a little closer. Oops. And you can kind of see there's some discoloration forming already at one of the electrodes. So I'm going to put these electrodes from my other battery into the solution, just so that you can see directly into the middle of that, into the middle of the wells. Okay? And by doing that, it just kind of helps you see what's going on. Now you can definitely see now there's clearly some coloration going on here, and I've kind of spread it around a little bit. And what's kind of cool about this is with the universal indicator, I can swirl it now. So if I swirl and keep swirling, you get a really nice set of colors there. Okay, and you're going, right now we're at greenish, and that looks like it's turning green. And that looks really kind of cool. Okay, when you watch it. Now, when you watch it, one of the electrodes, you're going to see color forming. Let me try it again here, and we can do it. And it's still going because the battery's still working. Okay, so the battery's still working. If I just place these electrodes right in the middle, you can see the coloration. You can see it producing color. Okay? And what's happening is it's reacting. And one of those electrodes you can see is turning purple. This electrode in black is turning purple, just like this electrode here in black. And then the red one is turning kind of a yellowish. Okay? So let's take those out, swirl again. It's kind of nice when you get the swirl. Purple, get a bunch of different colors. You see kind of a blue in there, a green. And it gets back to kind of a blue-green, okay? Now, I'm going to put the black electrode closer to the other black electrode just so we can get that same kind of coloration going. And you can see on one side it's turning yellow, on the other side it's turning purple. Now, why is it turning yellow? Because it's becoming more of a yellowish pH. Why is it turning purple? Because it's becoming more of a violet pH. So you're able to identify, at the violet, what should we be getting? That's right, base. And at the yellow, what should we be getting? That's right, more of an acid. Okay? Now, if I take that battery out of here, you could probably see at this electrode it's turning orangish, and at this electrode it's still turning violet. So you can see that we're getting a couple of half reactions occurring there. And what we're doing is we're driving the electricity through this circuit, but we're driving it against the standard against the non-spontaneity of this particular cell. So as you can see, one side is turning, this side, actually from my angle, you can see a nice orange. It's turning orange here, and here it's turning violet. Okay? And if we swirl one more time, what happens when we swirl? Goes back to a greenish. Well, why would it go back to green? Well, at one electrode, oh, just broke my electrode. Oops. I have to get my tweezers. Let's see if I got my tweezers around here. That guy out of here. Is it still producing? Yeah, it still looks like it is. Get another electrode in there. Maybe we'll get a little violet going on. All right, so why? Well, at one electrode, we're getting one electrode turns violet. One electrode turns violet. What does that mean? Base. So we're getting OH minus. The other electrode turns orange or yellow. What does that mean? Acid. H plus. So what happens when we swirl? Breaking. There we go. Okay, so what happens when we swirl? It turns green. Why would it turn green? Well, let's swirl again. Why does it turn green? Because at one electrode we're producing H plus. One electrode we're getting H plus. The other is OH minus. When we swirl, we get water. What's the pH of water? 7. And that's green. Violet, orange. Okay? Now, if we want to look at these half reactions, what's really hard is watching these videos like this. You can't see bubbles being formed. You're going to have to take my word for it, okay? But I'm going to show you those half reactions, and we're going to just balance the equation, and then we'll be done, okay? But it's really kind of cool. I can see right now it's still producing some orangish here, and we're getting some violet here. We'll be able to do it one more time. I've already got the half reactions written out. And let me just show you what they are. Okay. Maybe I'll go up above. How's that look right there? That way they don't get in the way. Okay, so we got two half reactions right there. Oh, you can see the color. Once again, we'll swirl. We keep producing H plus and OH minus, and it neutralizes again. Okay, let me just get one of these, and I just want to show you that one of the electrodes, you can't really see it, but you're getting you're getting gases formed. Now, we have two half reactions here. Okay, and both are written as reduction potentials. So we're using the battery to drive this in a forward direction. Excuse me, to drive it in a non-spontaneous direction. So at one electrode we're getting H plus, the other we're getting OH minus. Well, we have OH minus at one electrode, so what does that mean? This other one must be reversed. So this one has to be reversed. And that means when it's reversed, it's going to have electrons on the right side. So I'm going to just reverse it. H2O goes to O2 plus 4H plus 4 electrons. What is the voltage going to be? A negative 1.23 volts, because this is going to be our oxidation half reaction. This one is going to be our reduction half reaction. Now, we have 4 electrons when we reverse this one. Reverse. We have 4 electrons on the right. We have 2 electrons on the left, so we have to take this top half reaction and multiply it by 2. Once we do that, we're going to get 4 waters plus water here. So 2 times 2 is 4 plus 1 water here. Let's see, is that 2 O's? This should be 2 waters right here. So this should be 6 waters, okay? So that should have been 2 waters because you have 2 oxygens, 4 hydrogens, okay? So you're going to get 6 waters. Well, we're going to have 4 waters, but we have, and we reverse this one to be 2 water here. So we have to have 2 waters on the left. So now we're going to have 4 plus 2, 6 waters. Then, once we reverse it, we have 2 times 2, 4 electrons here, plus 4 electrons. Those will cancel. So the electrons cancel. The electrons here will cancel, okay? Because this one has been reversed. So now we're going to get O2 plus 2 H2s. 2 H2 plus O2. This is an arrow. Okay. Now notice, let me change colors here. This, you have 4H plus on the right, and when we multiply 2 times 2 here, this is going to be 4OH minus. So this is going to produce 4 waters right there. So we also get 4 waters. And then when we balance this out, these 4 waters will cancel, and we're going to get 2 waters on the left. So 2 waters produce 2 H2s plus an O2. And while you're watching this reaction, look, we're still getting red at the top electrode, reddish orange, and we're getting violet at the bottom electrode. And then you can see that blue in between. So then what's our cell potential going to be here? E cell is going to be E ox plus E reduction. Our top one is E reduction, so we'll just say E reduction plus E oxidation. Okay, and then we have a negative 0.83 volts plus a negative 0.123 volts. So when you add that up, you should get a negative 2.06, negative 2.06 volts. So this reaction is non-spontaneous, thermodynamically unfavorable. So how do we make it work? The only way we can make this reaction work is we need electricity. We need a battery. We need to make this. This is now an electrolytic cell. So we have to provide enough energy, and this battery has about 9 volts in it. It has to be a voltage greater than negative 2.06 so it can become a positive voltage and drive forward. So this is an example of an electrolytic cell, and it's very colorful. It's a great, simple way to show the process. So we got a negative voltage because this cell is normally unfavorable. The only way we can make it work is by using a battery. Okay, and last time we got a nice red, green, and blue. Let's swirl, and this will end our demo. If we swirl, we now get green. We just neutralized the acid that was produced at one electrode. The acid produced at one electrode, H+. We're getting OH- at the top electrode, H+ at the bottom. We could figure out which electrodes they are, but one is losing OH, producing OH-, one is producing H+. And from that, we're able to neutralize. Okay? All right. That's it. And I hope you have a great weekend, and stay safe.